Hello, everyone. Welcome to a new episode of Happy Hour with Architects. Today, we have two guests who literally need no introduction. I think we would not find a single architect who have got into computer architecture without reading the pioneer book, Computer Architecture, a Quantitative Approach by John Hennessy and David Patterson. I personally started with the computer organization book when I was an undergraduate. Please welcome John Hennessy and David Patterson, ACM Turing Award winner 2017. The award was given for pioneering a systematic and quantitative approach to design and evaluation of computer architecture, which actually had an enduring impact on microprocessor industry. Dave and John have been a lifelong pioneer for RISC-V. They founded the Open ISA initiative, the RISC-V Foundation. John had an extraordinary career at Stanford, not only as a professor, but also he served as the president of Stanford for more than a decade. David Patterson had an outstanding career at Berkeley, but he still contributes to research both at Berkeley and Google. Welcome and thank you so much for joining us. I really appreciate it.
Delighted to be here.
Yeah, more than a decade. He was president for 16 years.
Yeah, a long time.
A modern record.
As I joked with President Obama, goes, that's twice as long as I made it.
So I think I would like to start from the beginning. Like you two have this lifelong collaboration and friendship. So how did you two meet? How did you decide to write the book? How did you two decide on working together? How did that happen?
I guess we'll take turns. I think I started at Berkeley in January of 77. Did you start in the fall?
Fall of 77.
Okay, so we started about 9 months apart. And we met at I'm pretty sure we met at a DARPA meeting at the Berkeley campus, I think.
Yeah, it could have been. Or that, yeah, probably it was, because that was before we had that summer retreat. We had a joint MIPS RISC retreat, but that was later.
Yeah, so there was, what we call VLSI. DARPA had a VLSI program that was trying to get universities to take advantage of this new opportunity around Meade-Conway. And Berkeley and Stanford and others were funded by it. And there was, my memory is there was this Bechtel thing and there was this young guy giving presentation. I said, wow, who's that grad student? I remember saying that. And at the time, John had a beard and long hair, and I think I had long hair too.
Yeah, so that was the beginning, and I think in the early days of RISC, as many people know, there was a lot of opposition from various parts of industry who didn't buy the ideas for a variety of reasons, and I think we formed an alliance because we felt we both had this research experience. We thought the architecture and the approach was really compelling. And we were on the same side, so it was easy to form allies. And at that time, there were no other allies. IBM was completely quiet about the 801 project and what was going on in the 801. So it wasn't like they were rushing in and saying, "Oh no, these ideas really do work." They were kind of completely in the dark. We were in the dark of really what was going on. We knew sort of what they were working on, but not very many details.
And the kind of the mood of the time was very different from RISC. There was a movement called high-level language computer architecture, and the argument was kind of why was software so bad? Why was their projects not finishing? And the blame was that software had to do this gap between what people were programming in this low-level hardware, and if we could just raise up the instruction set level to be very close to what the programming language is, then by closing what they call the semantic gap, all kinds of things would be better. And that was the right way to do computer architecture at the time. And at the time, there was, a kind of a company that did that was Burroughs Corporation, and they had a architecture that was designed for algol, basically. And that was seen as the right way to do things. And the person who was the architect of that, is this Barton?
Yes.
Yeah, he received the Eckert-Mauchly Award, you know, and he was kind of like, this is the right, he was a visionary, that was the right way to do it. And then we were doing the opposite, right? We were saying compilers are a really good idea, you know, with Moore's law, we should try and keep things simple because it goes, and at that time too, microprocessors were not seen as the mainstream computing. Microprocessors were kind of toy computers, like, you know, you'd have in PCs or refrigerators or something like that. It's still the right way to build computers was you build them out of hundreds or thousands of chips, and they're big racks full of stuff. So we were saying that the microprocessor was the future, and these high-level instruction sets were the wrong way to do microprocessors. So it was heretical.
Yeah, there was even a government effort to make a process for evaluating ISAs, instruction set architecture, based on abstract measurements. How big was the code size? And code size matters, of course, but it's not the only thing that matters. How symmetric was the instruction set? So when you looked at it, the VAX looked like it was the ideal architecture.
Yeah,
The fact that typical compilers only used 10% of the instruction set didn't bother anybody, but it should have. It should have.
So I guess
the other interesting piece of history here, Dave, is we both had some experience with the microprogramming, microcoded world, where essentially, and people were trying to build compilers or translators that would eliminate the need to write microcode by hand because it was so hard and
reduce bugs.
Yeah, and reduce bugs. And it seemed to us, you know, if you can write a compiler for that, why not just compile directly to something that looks very close to what the microcode, what the hardware really is doing, right? Rather than do this translation step at runtime, extra work at runtime.
Yeah, but both of us, microprogramming was popular. Kind of the notion was that would let academics innovate below the instruction set level because, and you know, they were pleading with companies that were using microcode to make writable control stores so you could get it. And so my dissertation, and I guess yours too, I did a compiler and verification for a particular microprogram thing, but we were kind of right at that point where we had to, at least I had to invent a restricted higher level programming language to make it efficiently mapped to microarchitecture. But the gap between, you know, writing a program and compiling it to microcode and writing a straightforward programming language and compiling to a simple instruction set, that's a very small mental gap. Very, very important leap, but, you know, technically very small.
So I see like two teams merging.
Yeah, just one more thing.
Yeah.
In fact, the later VLIW work by Josh Fisher, he came from the same school.
Same school.
Microcode was 100 bits wide.
Right.
It had lots of fields, kind of VLIW-ish. And Fisher was, again, he was kind of compiling from microcode, and the inside is, oh, we could do, that could be a regular instruction set, and that's
Right.
VLIW. But all, and in fact, what micro that people publish at, it was originally microprogramming.
Yeah,
That's where my first
was.
technical paper was at the microprogramming workshop. The workshop on microprogramming. So they kept the name micro, although the people who attended the original micros would not understand.
Yeah, yeah. And it, you know, a similar kind of thing was happening in the microprocessor industry. People were competing by adding new instructions to their architecture, to the ISA, implemented in microcode, and charted written sequences. Programmers
I think we are maybe having a little bit trouble.
telling Zion this, we're in this constantly adding new instructions to what was the original core 86 architecture. So it was on.
Right now I'm using my phone, but as my internet connection because I couldn't get the thing set up. But oh, okay.
Yeah, I
Are
think
we
we
okay?
lost a little bit, but I think we're maybe okay now. Yeah.
Okay.
Okay, so I guess I see like two themes emerging. One is going to simpler ISA and adding the complexity of transforming in the compiler. And the other one is lack of evaluation at that time. Like, did these two actually motivated the book? How did the book happen?
Both, I was impressed with John, various meetings we go to, besides arguing on, the kind of the RISC stuff was in the early 80s. And but by 85, John had founded MIPS and I started consulting for Sun, which was doing Spark. So it was the technology transfer from academic ideas to commercial was underway. But we would get together at various meetings, probably DARPA meetings, and then complain about the textbooks. Just like, oh man, this is awful. And and this idea like, well, maybe we should try and write one together. And kept talking about it, kept getting postponed because it's going to be a lot of work. And then I could kind of read the tea leaves, and I could see I was going to become the chair of the computer science division at Berkeley. I was likely to get that job. And it was like, oh my God, I thought my life would be over. So suddenly we had a deadline. We had to finish the book before I started being chair. Otherwise, who knows when it would happen, right? Which is probably a reasonable, it was probably a reasonable assessment. And so now we had a deadline. So I think in 1988 or 89, we said, okay, this is it. We got to get started.
And I think we were both impressed with what Don Knuth had done with the art of computer programming, really creating a framework, a scientific framework for thinking about algorithms. And I said, well, rather than the textbooks of the time were what we used to call supermarket approaches. Here, one from column A, one from column B, one from column C, one from ILD, this sort of thing, without a basis to kind of compare and accurately assess the value of the idea. So we said, let's start with, and the CPU performance equation had come along, which we had stumbled on. I think had we discovered it earlier, we probably could have built a more convincing case for RISC early on, but we really didn't know it until later. But once we had that, we said, okay, here's a firm basis. Then we'll think about a firm basis for how to think about memory hierarchies. And so that really helped us then think scientifically about it.
Certainly the Knuth book was startling when it came out. It was revolutionary. We were both in grad school when it came out, and boy, when you got the book, it was like it made you think about algorithms differently. And my memory of the book is it was filled with quotes. I remember seeing quotes and just thought it was just the greatest idea. I went back and read the book. He hardly has any quotes, so I thought we were imitating him. And then when we started, we said, well, we started with a clean slate. What's the right way to do it? And I remember and we would take turns driving. It wasn't before the internet, but it was. We would take turns going either to Stanford or Berkeley and meet and talk about ideas.
And then we hung out at Deck Whirl for a
that's
bit.
right. That's right.
We hung out at Deck Whirl for one semester or so, and get together and work there.
So that was we could meet all day and talk, and that was a meeting place. That's right here in Palo Alto, and we got very excited about the ideas, and that over a few months, like, how are we going to approach this? And we took it really seriously. We felt like we're going to do this. We're going to affect.
Let's do it right.
We're going to affect a lot of minds. We got to get this right. And I just remember the ideas going back and forth. And I remember there'd be things John say, you know what? I think I'm going to explain out of order this way, right? I'm not going to do it like that. And the memory hierarchy stuff. I remember, we incorporated. Mark Hill was getting his dissertation with me at Berkeley, and he came up with the 3 C's. I go, man, that'll fit right into the book. And it's pretty exciting.
Yeah. I think the other thing we benefited tremendously from is a large number of members of the computer architecture community reviewed the books and gave us really good feedback, really insightful feedback. And they said, you know, this explanation isn't as good as it could be. And, you know, have you really thought about this issue and more? And that really helped us get the book.
Yeah, and we also did it like a computer, right? We had an alpha edition, which was basically, alpha was just kind of notes.
Alpha was torture.
Yeah, alpha was kind of course notes. And we got, you know, was it basket audit or one or two people tried to teach from the notes, but then we did a serious beta edition, and the beta edition was pretty good.
It was pretty good.
And people used the beta edition in the fall of '89, I think, in classrooms. And, you know, we made enough, maybe a dozen schools. I don't know, we have to look it up.
Yeah.
And they gave us all kinds of detailed feedback, and we made one more pass before the book was out. And, you know, we told the publisher, Morgan, when we selected the publisher, you know, we're going to do this, and you guys got to deliver because we've got a schedule, right? And they were used to authors, you know, saying, and they said, sure, kid. Okay, but we even said, look, we're going to have a deadline, and if you miss the deadline, there's a penalty clause. You have to make a donation to a charity if you don't make it. And we delivered on the deadline, and then they did.
Yeah.
They did too.
We also introduced a new concept to them, pipelining. They were not aware of that concept. So we would pipeline chapters to them. We would say, okay, you're going to get the first 2 chapters, you know, and you start editing those and doing your typesetting work while we produce the next 2. So
they were very skeptical, very dubious, because a lot of authors say this, and then, you know, it's only something like half of all books that they sign a contract get finished, right? So they're used to authors just, you know, being way late, and we got it done. And, you know, we had that deadline, and we finished. It came out. We turned it in by December of '89, and I started being chair, I think, June of it.
So from idea to the beta version, how long was it?
Less than a year.
Yeah, about a year.
That's amazing. That's amazing. Yeah.
It's in the forward of the first edition.
Yeah, the very first edition has there.
I don't know if you. I don't see you if you have one.
Probably I do somewhere.
Yeah. If you look at the forward, the first edition has all the dates.
Yeah, it has all the dates, and
because it's you know, in retrospect, it's pretty impressive that.
Yeah, so it was, but it was a pretty intense effort, and of course, the first edition is small compared to the later editions, so that probably made it a little easier to do. Yeah, you know, we thought of a lot of classical things in terms of how we organized the book, right?
And one of the things that we did, we put formulas. This is what physics books would do. This they have formulas that were important on the insides of inside covers, and so we put formulas there like a physics book. And I think the instructions said something back. Why we wrote this book? Yeah, I think it's towards the end. It gives the dates.
It probably is.
Does that say?
I don't know. That's why we also gave the $1 bounty for every error.
Right. that was from Knuth.
That was from Knuth. Yeah.
Knuth would give you a $1 bounty if you found a mistake in his algorithm book, which is a little more, more impressive.
Yeah.
And did he have an escalating scale or something?
No. I don't think that's just $1. Maybe later books was more. But one of the things we discovered, which he had discovered as well, most people never cash these checks. So you want to write them on an account where you really don't try to balance it, because people don't cash.
They would put them on the wall.
Yeah.
I think that makes sense. So I guess there have been multiple editions until then, and each edition, like you are kind of revising content, adding new content. So I guess from that time to, I guess now it's to 2022, like how do you feel the progression of the book?
Well, people still like it. So we, you know, I think that first edition was a breakthrough. I mean, it was, I remember Microsoft stored it. You could go into Microsoft and you could get like pens or papers or a copy of Hennessy and Patterson
in the
Microsoft storage, right? People bought them. Yeah, so it was not just a big deal in the universities, but in industry too. It was really, so it was such a contrast from before. I think the subsequent editions, people are still happy with them, but you know, I don't know that they've had. I don't know what it's.
Well, the first book had such a dramatic impact because it really reframed the way we think about computer architecture as a scientific discipline, and I think that really difference. Of course, over time, we moved a lot of that material down into the computer organization book because it became quite basic. I mean, undergraduates need to understand pipelining and caches and all these sorts of things.
Yeah.
So we could move more advanced materials in. The other thing we've always done is we've always said, you know, we want to talk about things that are in use in practice. So if we see something emerging in the academic side that's getting picked up by a company, then we can put it in there. But we have this, we're not trying to describe all the research because it's hard to, if you try to describe all the research, you'd get a book whose length is terrifying. So you can't possibly think about that.
And it's very hard to do a book like that well, because you have to decide, well, you know, even if you have great taste of what to put in, what's your explanation why you put in this person's you know's idea into your book? You know, why did you include his or hers and not mine? Right? Well, that's really hard to call. If we say it's got to be in a real computer, then that's a clear threshold. Like an example might be transactional memory is a recent example. A lot of talk about it. It doesn't, you know, especially when there's a lot of excitement about it and all kinds of work, it hasn't really caught on in industry, right? And so I don't think we have much about transactional memory in there.
Right.
But, you know, like in the latest edition, we added domain-specific architecture.
Yes.
We made that decision, you know, in 2016. That looks like a pretty good decision, right?
Yeah,
So, hey,
definitely.
I'm
right?
glad we got.
Yeah, that's right. That's right.
Yeah, what we would have felt bad about if we put something in that we felt like, well, that was a waste of time and energy. That really didn't last. It wasn't as impactful as we expected.
I think that makes complete sense. So I guess in my undergrad class, actually, I do talk about accelerators and TPUs and what other companies are doing. And I feel like students actually feel more connected to what's happening to real world instead of just talking about things that we invented maybe 50, 60 years ago. So having that modern things actually makes them quite excited.
And I think John and I, as teachers too, thought it would be easier to connect to students if we tied it to the real world, right? Is if we said, yeah, this is really in computers that you're using have these features. This explains why they work, how they work fast. And so I think we wanted to always maintain that connectivity.
Yeah, I guess let's just say that the book has major impact, and I guess we already talked about it. It's at the corner of every corner in the world. I am a living proof. So I guess we did kind of touch into computer architecture research and what is happening, what has happened, what has been happening. So I guess I would like to know that what do you think about the current state of computer architecture research and the community around it?
I could say something. You know, I think when we got into it, there was the Meade-Conway stuff that was very exciting. And so many of the papers that I wrote in that decade, we were building chips and doing computer architecture. You know, that was hard work, but boy, it sure felt grounded, right? It felt comfortable that to do that. And I would always quote, and I give this bad career talk, how to have a bad career. And in there, I quote John, and he said, you can always tell when you read a paper whether the authors had ever tried to build something and make it work. I remember John said, and I put it into my talk, but that kind of, if the difference is if you just design it, or like you do it on paper, or you kind of design it, but if you have to make it work, then you get religion about keeping it simple. Because, you know, with the bugs that show up and stuff like, then you get it. It's very hard to appreciate the importance of simplicity if you haven't had to design something yourself and put the features in and debug it and make it work. So yeah. So my fear is people who only use simulators, and you know, it's hard to build chips, but it's hard for me to see that you couldn't implement in FPGAs. They're even online, you know, you don't even have to buy anything. But so I think without the grounding of having to implement some of your ideas somehow, you can get disconnected from reality, and it's very hard why aren't people using my ideas? And why I've shown it's a good idea, right? Well, if you're not implementing it, it's hard to convince people that either it's hard to convince people to use your ideas, or it may be that you haven't had to implement it and debug it in some form besides a simulator, you may not understand some problem that you have.
So I think that's a great observation. And the thing I'd add to it is, computer architecture is a technology-driven field. We are driven, and we have ridden on Moore's law and the integrated circuit industry. And in fact, one of the advantages of being in this field in the 80s was integrated circuit capability was exploding and it was going through the roof, and Dennard scaling was all in place. And so really the job of the architect was to take that incredibly growing capability of integrated circuits and turn it into high performance, faster computers. And those technology changes are vital. I mean, one of the things that the prior industry had gotten wrong was they had designed architectures around the notion that memory was very expensive, because prior to semiconductors, it was core, and core memory was very expensive. I tell my students, that the big mainframe we had only had 128K, not megabytes, K, that's it. And so that change occurred. We're now in this late stage of Moore's law, breakdown in Dennard scaling. And so that's really forced us to rethink how we think about computer architecture, which is why the DSA is really some kind of domain specific thing is going to get there. And in order to make that work, you obviously have to change the software interface as well, whether it's a GPU or it's something doing deep learning of some sort. And that's injected some enthusiasm about rethinking things. We kind of pushed the conventional general purpose architectures about as far as we could push them, without changing the programming model more radically. And I think once you change the programming model, you get all new opportunities to rethink how you attack problems.
Yeah, I think the other thing, John and I were just sending back folks, the most recent Computer Architecture Today blog talks about microarchitectures, auto execution, and makes a quote that a 1% improvement in by an industrial strength simulator is a cause for celebration. Boy, I don't think, at least academic researchers, the accuracy of their simulations is, the error bar is much higher than 1%. Might be 10%, might be plus or minus 10%.
Maybe
so if you
more
think
than
you're
that.
making 1 or 2% contributions, when the error bar is 10%, you just don't know what that is.
Yeah,
So,
and you still have to implement it. So and given that the thing that's in short supply in modern chips is energy, is power, right? Who knows whether or not, when you really came on implementing that, whether or not you even get 1%, you might simply lose it completely. It might be negative.
So I think in the advice, kind of what's going on in the advice is, don't work on things that are single digit, where your goal is single digit improvements. Because it's just, even if you were to build a chip in academia and get it fabbed in the latest technology using students,
That's what Intel engineers should be working on.
Yeah, that'd be an Intel thing. Yeah, because you could very easily make a mistake, could be off 30%, and it wouldn't have in your final result, because so I'd encourage you to work someplace where there's much higher impact. And I think that's one of the places we've seen that is domain specific architectures. And so not only is there potential for much bigger impact, there's this desperate need for ideas. Because when I give a TPU talk, a standing question is, okay, machine learning, that makes a lot of sense. What other areas, right? And what we think the future is going to be servers with all kinds of accelerators in them. So, but this should be exciting opportunity for researchers, is they want people to come up with ideas of other applications that are worthy of accelerating, and then what's the right architecture for it. So this is kind of like the early days of RISC, is we had kind of a clean slate. What's the right way to do it? With domain specific architectures, it's basically a clean slate, and all kinds of different ideas could work. Right now, we've proven that machine learning is a good target, but man, a lot companies and venture capitalists are investing billions of dollars on that topic. I don't know if there's going to be a great opportunity for academic researchers, but there are all these other topics that need to be accelerated, and there could be big opportunities in these other ones.
So I completely agree with the great opportunity with the domain-specific accelerator, and also there is just so much opportunity to invent cross-stack, like how to design the compiler, how the programming language, how the application should talk to our hardware. So these are all exciting. And at the same time, with FPGA, it's so easy to implement stuff and show the performance, right? And even doing a chip, there are ways to do it cheaper and not necessarily spend a whole lot of time. On top of that, when I talk to my students, they actually gravitate towards building things compared to just running things on simulator, right?
That's the thing. Kind of faculty remember how expensive or hard it is, but it's exciting for a student to build a chip. What I think of the two things, especially for students, at least on undergraduate students or maybe grad students, is invent your own programming language, which is really fun to do. It's very little chance anybody will use it, but it's a fun thing to do.
Yep.
And build your own computer, right?
Yep.
You know, and especially it's got this kind of Christmas Day impact is you fab the chip and you cross your fingers, wait to come back, and then you plug it in. Does it work? You know, is it this going to be something that you use for jewelry, or it actually runs programs? But if you design a computer and it runs programs, it's very stimulating and exciting. So it's inspiring to students to be involved in a project where they get a chance to build things. And, you know, and I think in John's my experience, it's also tremendous educational value of, you know, seeing your ideas, trying to implement them, trying to make them work. It really teaches like the importance of clock rate and die size. And now that energy limits everything we do, I just don't understand how you can make a contribution and get a realistic impact on the energy without any layout of, you know, you don't have to fab it, but at least with layout that you could extrapolate what the power and energy would be.
So I believe I see all the time is ripe for doing this kind of real impact research. But then if we look at academia and look at the conferences, like not that many people are essentially doing it. So there is some gap there. Is it the mentality? Is it the pressure of tenure and etc.? Like how do we reflect it on our community that people are excited to build things?
Well, you could look up my bad career talk. I mean, so I think especially, you know, I think it's my saying is that for better or worse, benchmarks shape a field, right? Mm-hmm. So I think a bad benchmark is citations. Right? I think if what you want to do is have big impact, it's not writing the papers with the most citations. Sometimes when you have a big idea, it leads to a lot of citations, but it's a side effect. It's not the main goal. So, you know, if you're as a member trying to publish 20 papers a year, I'm not sure you got 20 high impact ideas. So, you know, I think I would concentrate more on a few that are really, you know, big ideas that could change the world, and then evaluate them really well. It's a little, you know, that'll be a different path. Now, I hear all the time the excuse about tenure. Tenure is a very small fraction of your career. Okay, if you think it's at your institute, it's you got to play the game and get a ton of papers out. Okay, that's an excuse for about 5 years. After that, if you want to have impact, you should tackle bigger problems and evaluate them more seriously. Things that are going to have much more than a 1% difference. But you know, that's kind of, you know, you have to make that decision. Are you going to try and have win the most paper award at SIG-Arch, or are you going to try and have the impact? And I can say that, you know, in terms of awards, they don't give awards for the most papers or the most citations, right? The awards are actually on this harder thing, which is impact. And the way the awards work is you can get people to write, if you have real impact, people can write letters documenting the impact, which is, it's kind of softer than citations, but that's what people care about. From an award perspective, it's how, typically, since I've been on the Turing Award Committee now, a typical profile is people do something contrary to the conventional thought at the time and prove it right and eventually have high impact. And that's in theory, it's not just architecture, all these fields, that's a very typical scenario. So you're doing something not that everybody else thinks. In fact, people are skeptical you can pull it off, and you pull it off and it turns out to be something that really makes a big difference. So if that's your goal, you have to decide what your goal is. But if you want to, it's a lot harder, a lot easier to have high impact if your goal is to have high impact. If you're, you'd be very fortunate if you're just trying to produce the most papers and one of your ideas is revolutionary. Good luck. That'd be great, but I don't think that's typically what happens.
Yeah. I think also, as you pointed out, we are in an era where looking at the full stack is the way you're going to make advances. So that has the opportunity then to form collaborative research groups so that people work together. And if I look at especially the early work we did on MIPS or the work we did on multiprocessing after that, both of those had teams of people. There were people who were bringing compiler expertise to it, people were bringing VLSI expertise to it, people who were thinking about the ISA. Design tools, we designed a bunch of our own design tools. Half of my initial students did design tools for their initial thesis work, for their PhD thesis work. And same thing later. In fact, Mendel Rosenblum built SimOS so that we could test out the operating system for the hardware we were building. And that became a small company known as VMware. So there are really interesting insights like this that you can get in this kind of collaborative full stack approach to thinking about work.
Yeah, I've always, as part of my bad career talk, what I say is I think in academia, what's hard for industry to do, especially now that I've been there a little while, is do cross-disciplinary stuff. It's really hard for them to do that. But they have tremendous strength in any narrow area. But getting a manageable size group to innovate across disciplines is really hard. That's really easy for academia, right? We kind of a faculty consists of experts in a lot of individual experts. Put them together in a team, and you can innovate across these boundaries and have real opportunities for high impact. And so, yeah, I would say I think a team building would be an important skill to have, being able to get people to work together and towards a common goal. And I think there's lots of opportunities there, especially, these are great times for research, at the ending of Moore's Law. Shockingly, our whole career, we got to use Moore's Law. That's over. We're starting to work on the revision of the textbook. A lot of things are ending, right? Disk drives are really slowing down. A key characteristic is called areal density. They're now down at, it used to be, I think, 50% a year. It's less than 5% a year.
Yeah. Well, they had their Moore's Law run just like Moore's Law had it. And they had a period where they were increasing, they were doing better than the semiconductor industry actually in terms of density. But it didn't last, right?
Yeah, and so now what they're doing, how do they get more capacity? They're putting more platters in the drive.
Right.
And so in the last edition of the book, it was 5 platters. This edition, 10 platters. That's not exactly innovation, right?
Well, no, it's back to, they used to have 10 platter drives. Yeah. They went down in size when they went to Winchester.
But what they're just going to get is they're not going to get fat. The bandwidth is not, the capacity is going way up.
Right.
Because they're putting more platters in, but the bandwidth is not good. And then DRAMs. Apparently, we were at, state of the art is 16 gigabit DRAM. The next one's going to be 24 gigabit.
Yeah.
It's not going to be an exponential for the first time.
Well, DDR4 was several years late. DDR5 is more than 5 years past what the initial projections were.
So we're just seeing all these fundamental technologies kind of grinding to a halt. Where I used to marvel that, wow, what a cool field we're in. Is that all of our technologies are improving so fast. It's not like aircraft engineering or auto engineering. This is going to make technology. Here is a bunch of things that we depend on better are going to start barely getting better, and so that leads opportunities for computer designers, right? If the underlying media is not rapidly improving, how do we get much better compute? We still need much better computers. We need faster computers. I think it's more in the architecture realm.
And software. I remember many years ago, I asked Maurice Wilkes, who was, I think, the last living pioneer, the original ENIAC, early days of EDSAC and things. And I said to him, Maurice, what's going to happen if this semiconductor thing and Moore's law slows down? He says, then people are going to have to be a lot more careful about how they write software and focus a lot more on efficiency. And I think we see that right now. For some software, it doesn't matter. It matters a lot if you look at these big deep learning problems, for example, or you look at GPUs, it matters a lot. So we've had to refine the software, and that probably needs to move up more of the stack over time, particularly for other kinds of compute intensive applications.
I guess with the opportunity of building new chips, I guess let's kind of talk about the RISC-V Foundation and the OpenISA. Like, how did you decide to go for it and make that foundation?
Yeah. So let me give the correct story here. So we had started the PAR lab, one of these exact multidisciplinary labs, absolutely people from different expertise, including applications, all in one lab. It was funded by Microsoft and Intel. Krista Sanovich, who graduated from Berkeley and was at MIT and came back and was involved in parallel, said, we need trying to re-implement existing architectures or MIPS and stuff like that. This isn't going to work because we knew we were going to have to innovate because with the ending of Moore's law, we're going to need acceleration and stuff like that. So we don't get much benefit from a standard commercial instruction set. We should do a clean start. And I said, I was skeptical this was the right thing to do. In the past, we just used MIPS, trying to get some leverage there, but he said we could do it, and it would only be 3 months, he said. So I said, okay, go for it. And so he and Jensep Lee and Andrew Harman, 2 grad students, start working on it. It took quite a bit longer than 3 months, but what the good part about it is it was because they had a clean slate, and it took them a while, they were simultaneously doing the instruction set and building chips. They had a really good framework called Chisel, a much more productive language. So they were building chips continuously while they were doing the instruction set design, and it took a couple of years to do it. So kind of the Berkeley standard is, Berkeley's tradition is everything is open source and shared, right? That's going back to Berkeley Unix. So we did that. And so why did we do that? We thought other academics were going to want to use, for the same reasons we want to do, we thought they would want to. And why do we, each of us invent our own instruction set, or why don't we use ours? There was almost no academic interest in our using our instruction set. I also have to say about where the RISC-V name come from, because there's a story associated with that. So in the 1980s, there were basically 4 RISC chips that were done in the 1980s. And I called the first ones RISC-1 and RISC-2, and the second one was called Smalltalk on a RISC, or SOAR, and the last one was symbolic processing using SPIR. Right. Okay. And I went to a Turing Award meeting at ACM that was in San Francisco, and there I bumped into Niklas Wert, the designer of several programming languages. He said, if I had to do it over again, I would have called it Pascal 1, Pascal 2, Pascal 3, Pascal 4, like Fortran did. And it kind of was a marketing thing. He says, and I said, I had that same thought. I wish I'd called them RISC-1, RISC-2, RISC-3, RISC-4. And so I told the Berkeley people that story, and so they knew that story. So they decided they'd call it RISC-V. So I think because it's RISC-V, I'm getting more credit than I deserve. I was in charge of the lab, and I gave sage advice, but it was really driven by Chris on that. So what happened for us about 4 years into our efforts, lack of uptake in academia because they didn't think it was practical, we started getting questions about our online course material from people overseas saying, well, why did you change your instruction set? And it's like, hey, well, people complain about universal time, but why do you care about our instruction set? And then they made it clear is that there was a need for an open architecture that many people could implement. And I think it was actually people in India who started the conversation at IIT Madras. They wanted to have a national instruction set for India, and when they looked around, they thought RISC-V could candidate. And once we kind of understood that there was this need for an open instruction set architecture, we thought that was a great idea. Then we were all on board, and then that led to the RISC-V Foundation, which is now known as RISC-V International. And it was done in 2010 when the project got started. So now it's it's very popular. I think it's probably the third most important instruction set after ARM, and if you assume there's one ARM instruction set in x86, it's just 5. There's 200 members, companies involved, and, virtually almost all the big ones. So I think it is now launched, right? I think that's my risk. Did that cover your questions about risk? I know. What do you think, John?
Yeah,
Yeah,
John,
no, I think I think the one of the things I learned in this was it was tremendously difficult to get an established company to open up an architecture that they already had out there, because there were good arguments to do it, but ARM wouldn't do it. Nobody wanted to do it because, of course, that partly they were making money that way. There's always a fear in doing that, and I think there was also a concern about whether or not an architecture that belonged to a company, even if it was made open and license free, whether or not it would be an even playing field. And that was a concern, which is, I think, the real reason to get the RISC-V Foundation and kind of embed that ownership of the architecture in a neutral party. And that I think has worked really well. And I think it's, I think what we've seen is that given this incredible plethora of wide range of devices that are being built, that really made the RISC-V timing ideal, because all of a sudden lots of people were going to build processors, not just big Intel desktop, kinds of things. You were going to have lots of processors everywhere, and having an independent open architecture, especially when you were talking about chips which might sell for $5 or $10, then having large license fee architectures didn't make any sense. So
and it was that transition from buying microprocessors, right, where you're buying chips and I'm putting chips on board, to I'm designing a custom chip and then I need IP to put in. And ARM kind of pioneered that. They weren't the only one, but they did a great job at that. They showed you could do that commercially. But once the idea was, if we're buying chips, we should be buying them from Intel or AMD or whatever. But if we're buying IP, that's more like software. So that could be open. And the instruction set specification can be open. So it lets all kinds of people compete. So you can either get open implementations, or you can go to companies and getting industrial strength versions. And that whole thing opened up. But it is all, it's kind of what classic computer architecture used to be, just instruction set design. So it's really that important interface, making that open, has enabled all this stuff. And an exciting vision is, plausibly, we can have the same instruction set in everything, in every computer, right? There's no technical reason, bigger addresses, but supercomputers, embedded things could all have that same instruction set. And that kind of fires up the RISC-V community. It's kind of like a religious fervor.
Yeah, and we'll see what happens over time, whether different versions of the architecture get implemented, and the leakage occurs over time.
Yeah, well, the either technical concern or the marketing efforts are, well, can we have a common community when there's specialization of instructions? Right. Can we manage that? And we're kind of doing this experiment where we're relying on volunteers to do work that if you're at a company, you'd hire people and tell them to do things. Can we get all the software there? Can we get all the right instruction set extensions? Can we do this as a community in computer architecture, as the operating systems people have done and the compiler people have done very successfully, open implementations that everybody shares? Can we do that same thing in computer architecture? And, we'll see how this turns out.
Yeah.
And
it
with
may
the chiplets,
it may not matter as much. It may not having, the thing that really drove common ISAs in sort of the desktop and laptop era was shrink wrap software. But now there's lots of processors that are being built that are not going to run shrink wrap software. They don't have to run Word or Excel or anything like that, right? Or they're going to use Google Docs, so it doesn't matter anyway. But in any event, that has pulled out some of the kind of need for consistency and complete 100% compatibility. And that, I think that'll continue to affect things as we go along.
Yeah, I personally think we are yet to see the prime time for RISC-V. Like this is just the beginning. And with the chiplets, like we have the ability to mix and match now, like, right, just as IPs. So I think we will see a lot of more adaptation soon.
And then, you know, taking it back to research, our original motivation was to make it easier to do computer architecture research, is that you can have an open instruction set, an open implementation, and a full software stack, a very rich software stack. So if you have an idea on that where you innovate in a piece of it, this is a really great starting point to be able to experiment in a pretty realistic way, and it can be done in FPGA. So you can have this full software stack, a full implementation, put in the ideas that you want to explore pretty cost effectively and kind of very convincingly. And increasingly, there's a RISC-V community willing to use your idea. So what I like about it, it's like the way I think of operating systems with Linux and compilers with LLVM and GCC, is you can do research and put your ideas into the thing that everybody's using, which is, you know, again, inspiring to students and to faculty.
Yeah, it's very exciting. So I guess you did mention about future research. So most of our viewers are actually students looking for new research topics, and they're trying to figure out where they should put their focus on. So I guess my question would be, where do you see computer architecture research going moving forward with the ends of Moore's law? And some insights on what to work on for new students.
Domain-specific approaches are going to be the future given Moore's law and stack in order to get more performance. Question of how can you build a DSA that can accelerate? We know how to do this for deep learning, for example, and TPUs and various GPUs can do this. But there are lots of other applications out there where you'd ask, and thinking about it from a practical viewpoint, I'd say, well, I may not be as good as your custom DSA that's designed just for this one application, but let's suppose I can do a whole range of applications within a factor of 2. Well, that's pretty good. That makes an interesting marketplace. So figuring out how broad these applications can be while still maintaining high levels of efficiency, I think is a really fascinating problem.
And it ties really well with semiconductor, right? What's amazing about this technology, if you wanted to build one processor that's the best in the world, you use, 3 nanometer technology to build it. But once you built one, you can stamp them out by the millions. So the idea that you could, this is the downside of DSAs. If you make it very narrow, then there's a large non-recurring engineering effort to build a chip, and if you need 10,000 of them, that may not make any sense. But if you can follow John's idea and kind of broaden, so there's more things that this can do, so that you can get the volumes up, that has huge impact. Given semiconductors is our media, which is a manufacturing, can stamp them out by the millions, and that'll have big economic impact.
I think we have also faced a lot of interesting questions about how we build software. Given that we're moving to this heterogeneous environment, right? I mean, you look at an M1, right? An Apple M1, and it's got fast processor, slow processor, it's got a GPU, it's got a little machine learning. Apple has the advantage that they own the entire stack, so they can make it work. But that's not going to be the approach that most people in the world are going to use. They have to combine software from various parties in order to get something that works efficiently. Well, now you've got a really interesting problem. How do I decide whether to use the fast CPU, the slow CPU? How do I allocate resources? How do I align things and make use of the domain-specific parts of the architecture? I think we have there's a lot of work run between software and hardware. And I think you're going to have to advance both to really make the kind of progress that we all hope for.
I think there's some other orthogonal things, and that haven't always been a topic of computer architecture. I think over the last decade or so, there's been efforts in security. I think, for those of us who've been in the field a long time, it's embarrassing how bad security is, that our technology is pervasive, but it empowers criminals all over the world, to attack people. It's a terrible problem that we're partially responsible for. If we have to wait for, it used to be, used to be this theory that program verification would allow us to have perfect programs and that wouldn't have bugs. I don't think that's going to happen. I think software is going to keep having bugs. So, and which leads to attack vectors. So it may be that we have to do things in hardware. We have to do checks every nanosecond, or we could do that to make things much more secure. I think having friends in the security community, a lot of what they do is point fingers. Hey, Microsoft, look at the big mistake you made. I think I'd like the security community to start being in the, let's put systems out there that try to be secure and let other people try and attack them, that go into kind of the synthesis of security. And I bet hardware is going to play, architecture is going to play a role in that. So not only the flaws in architectures, the Rowhammer and Spectre and Meltdown and stuff like that, not only kind of avoiding those flaws is actually helping lead the way. Can we plausibly have computers that were secure? In the early days, there was a lot of stuff around trying to make things more secure. There wasn't a big market for that, so that kind of like atrophied and went away. But that used to be a topic that people worked on. And my intuition is if we're going to end up with more secure things, the hardware's going to have to. And I absolutely believe it didn't used to be true. What they used to say is, from security, people aren't willing to pay for it. I think that's different now. I think people are willing to pay. If you had something that, let's say, it was twice as expensive and it was genuinely secure, there's definitely a market for that.
Particularly if it wasn't twice as hard to use.
Yes,
so that's right. The other thing. We've got to make security the default, right? So that people use it all the time. And we have a lot of work to do as architects. The rate at which side channel attack papers are coming out, there's one a month that I found a new side channel attack on something, right? I just read one using way prediction to do a side channel attack. Holy Moses! I mean,
Holy
this is
smoke.
incredible.
Holy smokes.
Yeah. So there's a lot of interesting work to be done there, I think. And I think it's going to be an exciting time, and finding things and really the best architects are people that have good understanding across multiple dimensions of whether some people are friends of the electron, they're going to go from ISA down to detailed circuit and think about how to optimize that. Some people will move up the compiler chain or even up to the operating system side and think about how to optimize that. And I think that's where a lot of the most interesting work is going to occur.
And if you're going to do domain-specific architecture, you have to move up into the domain.
You have to.
And that's one of the fun things about being at Google is learning about this machine learning domain is it's very pliable, which is I'm not used to that. I'm used to software being king and you can't touch a line of software. You have to innovate below it. That's not the case for domain for machine learning. They need to hit their quality score, but are perfectly willing to modify their model as long as you maintain the quality score. And it turns out the actual source code is not the millions of lines of code. It's it's thousands of lines of PyTorch or TensorFlow, and then millions of data, millions of data. So you're training it, so that makes it a little bit more pliable. So that's another area that you can innovate, but you're gonna want to.
Yeah, I think one of the things about this area is to see, despite deep learning still a relatively new technology and changing at an incredible rate, nonetheless, it makes sense to build architectures that accelerate it, even though we know that 3 years from now, the algorithm is going to be different, there'll be some changes, but can we get core primitives that will remain useful, perhaps not at the same level of efficiency as when they were designed 3 years ago, but will still be useful and have value. So
we
it's
talked about,
another
yeah.
kind of. Okay.
I was going to say that we talked about accelerators, hardware, software, co-design, security, cloud. Any comment on sustainability?
Are too high by a factor of 100,000, which is not something I ever expect to see in a. So we got to get these numbers right. But kind of say about that now that we've investigated machine learning, the training phase of machine learning, which is probably not a major problem. That's probably not, in part because people are building innovative hardware and they're working. It probably, it's worth keeping an eye on. Probably a problem is the manufacturing of computer chips, particularly for things that have short lives. For example, smartphones. Last year, 1.5 billion smartphones. 1.5 billion. We only have 7 billion people on the planet. 1. And not cell phones, smartphones. There's also a few hundred million feature phones, but 1.6. Now there are 6.6 billion smartphones being used, on the planet. And if they have a lifetime of 2 or 3 years, that's got environmental impact. And so it's either referred to it as the, I think, implicit costs, or sometimes called life cycle costs, or it's in the actual terminology from the environmental community, they call it scope 3. But, thinking about that now, the stuff I do is closest to the data center at Google, and kind of interestingly, doing stuff in the cloud has a bunch of advantages. Their lifetimes are much longer, maybe 5 or 7 years in the clouds. And the energy sources are much cleaner in the cloud, can be much cleaner in the cloud. It turns out it varies a lot by geography. And if Google places some of its data centers near high renewable energy sources so that 90% of the energy is clear. So within the United States, Nevada, less than 20% carbon-free energy. Oklahoma, I think that's less than 1,000 miles away, 93% carbon-free energy. So you can make almost factors of 10 difference in how clean the energy source is in the cloud by just picking the green location. So there's a big opportunity there, and my experience, people aren't so aware of it. It's a pretty new area. There's been some work at Facebook and at Harvard in this thing, but I think we do have issues within information technology that we should tackle. What I would love in the scope 3 things is really what you need as an engineer is to be able to make trade-offs. You would like to know, if I use this component, what's its carbon implications and energy, or this that other component, what are they? And right now we don't have a catalog of that information. It's very general numbers. Like, I feel like it's like, how many chips did Samsung make and how much energy do you use? You divide the two, you say, okay, Samsung chips use this much energy, which is not very, very useful. So I think that's another area that, I think, climate change is really important. Mm-hmm. Community has a role. It's not as bad as, it's not as bad as the airline industry. I'm kind of more environmentally aware. I also am, and as I said, the airline industry is a major problem. Getting on airplanes to fly to program committee conferences and having however many conferences we have a year, all in different geographic locations, no co-location. I don't know how responsible that is. I'm certainly going to give a lot more talks. I'm going to get on airplanes and go give talks. We have proved during COVID, you don't have to be, it'd be better to be there, but it's pretty good to do it remotely. And I think we should be thinking about how we should be doing our conferences and what we can do to reduce the carbon impact of our conferences. It's been great that it's at least those hybrid approaches. All kinds of grad students get to attend that they wouldn't otherwise. Yeah. Lots of people. So I think we have to turn this kind of as responsible. We have to turn this kind of problem into a feature and see what we can do to really reduce our carbon impact, because these airplane trips are serious. I think that'd be, could we get away with one airplane trip a year for faculty going to conferences? Suppose that was a requirement, what would we do differently? Right? I would assume we would have co-location you know, that we would bring things together. But and that could have other benefits. If we had common deadlines, maybe faculty wouldn't try to write 30 papers a year, right? if the
or all the conferences would be in Oklahoma where there's lots of green energy.
Yeah, there you go. Yeah,
You could, or now I have this vision of this incredible AR VR system where it's as good as being there in person, which we're not even close to.
Yeah,
we're not even close to, especially not for larger groups, right? One-on-one, we probably can get something, but boy, that's an interesting research problem.
Yeah.
Yeah.
An AR that's as good as attending
the conferences.
Yeah, so I guess we did talk about few research directions, exciting directions for the students. So any last comment before we actually conclude?
You know, I think John and I tried to convey our enthusiasm about the book in 1990, that this is an exciting field. It feels just as exciting right now, kind of with the ending of Moore's law and all of these, you know, how impactful are things is, and this desperate need for innovation, right? I think we were fortunate. Our timing was pretty good.
Yeah.
When we graduated, you know, with the early days of the VLSI and plenty of opportunities. I think this is another exciting time in computing overall, and in computer architecture in particular.
What's always been exciting about the field is the ability to operate across boundaries between how compilers work, how operating systems work, how the underlying hardware works, how the VLSI technology does. And I think the same thing is here, with even further up the stack and migrating further up that stack. And that's what's going to be interesting and enable people to do really innovative work. That's the fun in the field.
Yeah, I guess that's a good conclusion. I guess,
great.
Yeah, exciting times ahead. And with that, I think that's a good place to finish. Thank you so much for your time. I really appreciate it.
Good. Thank you.
Thanks.
Enjoy your happy hour.
It's a morning happy hour.
Yes, exactly. Okay.
Okay,
Bye
yeah,
now.
thank you.
Thank you.